All right, hello everyone. Welcome to today's online seminar. We will be doing some hands-on work today. If you feel like following along with the software carpentry lesson we'll be using, I've put the links on the slide and in the chat. So let's get started today. Today we will be focusing on getting your data tidy. And as a note, this session is being recorded and you'll receive a notification when that recording and the slides are available. So I'm Julie Goldman, Research Data Services Librarian at Countway Library at Harvard Medical School, and I offer a lot of these data management trainings, but I'm also available for consultations on best practices for data management plans, or if you need to find data for your research or project. Also, for the Longwood Medical area, the Research Data Management Working Group has a website full of resources and information, and our working group includes members of the LMA community from many areas, such as the library, information technology, research computing, our research cores, and affiliate hospitals. So I highly suggest you bookmark this website and reference it as you need. So let's review today's learning objectives. First, we'll understand what it means for data to be tidy. We'll recognize and resolve some common spreadsheet formatting problems. We will use the R package Tidier to transform some messy data into tidy data. And I'll provide some additional places where you can find some training and additional help. All right, so here is an example of the research cycle. And for this seminar, we are focusing on the transition from raw data to our results. And a key step in preparing data begins when the data is originally entered and stored, typically in tables, because this has an impact on the way we look at data later in our analysis. And much of our time will be spent in this kind of, data wrangling stage. Using our raw data, we usually can't jump directly into that visualization and statistical modeling. We first have to clean our data, which typically includes restructuring, filtering, transforming, aggregating, sorting, or merging our data with other data. And our clean, tidy data is the step along the way to our data analysis. And tidy data can be applied across all data types, and it provides the standardized structure that makes our data easier to work with. So good data organization is kind of the foundation of much of our day-to-day work. Most of us have data or do data entry in spreadsheets. What type of data you collect really depends, on your domain or experiment, and there are often guidelines from metadata standards on how you collect that data. And spreadsheet programs are very useful graphical interfaces for designing data tables and handling very basic data quality control functions. And spreadsheets encompass a lot of the things we need to be able to do with our research data. For example, we could use spreadsheets for data entry, organizing our data, subsetting and sorting our data, and even doing some statistics and plotting. But the most common mistake made is treating this spreadsheet program like it's a notebook. We typically, may rely on context or notes in the margins, the spatial layout of data, and fields to convey some information. And as humans, we can interpret these things, but computers cannot. And unless we explain to the computer what every single thing means, it will not be able to see how our data, all fit together. Specifically, computers don't understand those notes or any sort of formatting or color coding. And calculation, graphs, and tables, embedded within our spreadsheets are often inefficient. And then one of the main issues is how we structure our data in our spreadsheets. The main concept we are going to focus on today is turning this messy data into tidy data. So here on the screen is an example of what we may consider as messy data. Here we see that there are multiple data tables on one spreadsheet. There is metadata captured within the table. We see formatting and coloring has been used to indicate some information. And there are notes within the same space as the data tables. So looking closer at two of these data tables, we also see the column headers are values, not variable names, the plot numbers. There are multiple variables stored in one column. These tables have combined the species and sex into one column. So variables are stored in both rows and columns. There are multiple types of observational units in the same table. And there is a single observational unit stored in multiple tables. So we could combine these tables to make it easier to analyze the full data set. And with some formatting, we can transform this messy data into one tidy data set. So here is that transformed data set. We see that we have combined all the information captured in those two previous data tables into one. Here we have broken the date into a nice year, month, day columns. We have taken the plot numbers, which had been column headers, and created a new variable for the plot location. And the species and sex variables have been broken up. And the result is a pretty tidy data set. So exactly what is this concept of tidy data? So statistician Hadley Wickham coined the term tidy data in a widely cited 2014 paper. And he has developed some statistical software packages in R that are among the most used by scientists and businesses around the world. So data that satisfies these rules is known as tidy data. So each variable forms a column. Use one column for one variable. Each observation forms a row, so one row for one observation. And each type of observational unit forms a table with one value per cell. So one cell for one value. So here's what that looks like with each variable in its own column, each observation in its own row, and each value in its own cell. So a tidy data set is, by definition, about only one type of thing or event, such as an observational unit, that has been observed a certain number of times, equal to the number of rows you have, using certain measurements and identifiers equal to the data set variables. And you may have heard of this referred to as long layout or long format. So on the slide, we see examples of wide versus long formats. And wide format is considered messy because for the wide format, each row is often, a site, a subject, a patient, and you have multiple observation variables containing the same type of data. These can be either repeated observations over time or observation of multiple variables, or maybe a mix of both. So ideally, again, we want one column for the observed variable and the other columns are our ID variables. And this is our long or tidy format. You may find, data input may be simpler, or some other applications may prefer this wide format. However, many of our functions have been designed assuming that you have this longer formatted data, because the long format is more machine readable and is closer to what we typically see in the format of databases. So the participant ID variables in our example data frames on the slide are similar to the fields in a database, and observed variables are like the database values. And researchers often want to reshape their data frames from this wide to longer layouts, or vice versa. So in the remainder of this webinar, we are going to work through an R tutorial to help you efficiently transform your data shape regardless of what that original format is. All right, so today we will work through parts of this software carpentry lesson, R for reproducible scientific analysis, of course, in 1 hour. And now, in 50 minutes or so, we can only focus on one aspect of this full lesson, but these materials are freely available to you, so you can go back and work through everything on your own. So we are first going to load some data into RStudio, in which I will stress some good data management practices. Then we will use R functions to reshape that data. We'll use pivot longer and pivot wider, which can take a data frame that specifies precisely how metadata stored in column names becomes data variables, and the other way around. So I will, if you would like to follow along, at this point you should open your RStudio application, and then you can have the lesson with you as well as we work through these lessons. All right, so I switched over to my dual view where I have RStudio open on the left, and then on the right, I have the software carpentry lesson that we'll be walking through today. So first we're gonna go through why we want to use RStudio. And RStudio is great for project management. So as we may know, the scientific process is naturally incremental, and many projects, start life as maybe notes or some code, and then you create a manuscript, and eventually everything maybe, mixed together. So managing your projects in a reproducible fashion not only makes your science reproducible, but it makes your life much easier. And, most people may tend to organize their projects like this with a bunch of files and folders. And, this isn't ideal. There are many reasons why we should avoid this. It's really hard to tell, where things are, what versions of data you may have. It's just messy. It takes you a lot of time to find things. So a good project layout will ultimately make your life easier. It will help the integrity of your data. You'll be able to find things easierly, more easier to share with other people. You can upload, files or code or other supplementary materials with your manuscript, and you can easily back things up. I talk about all of these best practices, especially file organization, folder organization, file namings in previous webinars. So, fortunately, there are tools and packages which can really help you manage your work more effectively. And that's one of the most powerful and useful aspects of RStudio is its project management functionality. So we'll be using this today to create this self-contained reproducible project. So if you're following along, I hope you have RStudio open. So we're going to create a new project within RStudio. To do this, we go into RStudio. We go File, New Project. I'm not going to save what I'm working on. I'm going to create a new directory with a new project, and you can title this whatever you would like. I'm going to call it my tidy project, since we're talking about tidy days today. That's going to create a subdirectory on my desktop, and I'm leaving the create a Git repository checked. So then I create this project, and I see that RStudio is switching over to my project, I can see that it's created my project on my desktop, and I have navigated into it. All right, so next let's just talk about good practices for structuring your data files within a project folder. And this is a really great article on good enough practices for scientific computing. It gives some of these recommendations for your project organization. So for example, we should put each project in its own directory named after that project. We should put text documents maybe in a documents folder or directory. We should put raw data and metadata into a data directory, and then files generated, during the cleanup and analysis process should be put in a results directory. You could also call these, raw data and analyzed data. The key takeaway here is that they are, indeed separate. And then you could put your source for the project scripts and programs in a source directory, any programs that you use in a bin directory. And then of course, remember that name your files and folders to reflect their content and function so that they're able to be easily identified. All right, so we're going to use that kind of structure to save data in a data directory. So we're using this Gapminder data. And if you already have it downloaded, then you can just move it from where it is. But I'm going to download this data directly from here. So I'm going to right click on this link. I'm going to save this link as. And we want to make sure that we are downloading this data into our Tidy Data project and in a new folder called data. So if you need to create a new folder within your project, you can create a new folder. We'll navigate to that folder and then make sure we're saving this Gapminder data. As you see at the bottom, it wants to save it as a text file, but we want to be working with a spreadsheet. We want to be working with columns and rows, spreadsheet data. So we're going to save it as a CSV, and it will automatically parse out that text using commas to create that data structure. So I'm going to save my Gapminder_data.csv to my data folder within my project, and we see that it downloaded. And then we could also check in RStudio if this indeed happened, navigate into our data folder, and we could view this file. And yes, indeed, we've pulled in some text, but it is delimited by these commas. So we successfully have created this, pulled in our data. All right, another thing we want to do before we start working with our data, it's very useful to get some general idea about the data set that we're working with. And we can do this on the command line before loading it into R. And the great thing about RStudio is we have a terminal, right, built in. So I've been working on this before, so I'm just going to clear my terminal up. And we can use some basic, functions on the terminal to get some information about this data. So if we wanted to look at, the size of this file, what's great is we can try this out. We can list the contents and get some detailed information about our data. So we're working with this spreadsheet within our data folder, our Gapminder_data.csv. So we can look at how large this data is. It's 80K. We can also look at, how many rows does our data contain. So we would do, the function WC with some extra information listed out. We see that it has 1,705 lines. And then if we wanted to inspect what the data looked like, we can look at, you know, the first few rows using head. So we see this shown in two places. In our terminal, we can look at it, and then we've also read it in within our studio. Great. So now that we have, you know, our data in our downloaded, we are ready to get working with our data within our. So I'm going to switch over to the next exercise that we're going to focus on, which is the data frame manipulation with the Tidier package. So we've kind of already talked about this to understand, you know, the concepts of wider and longer data frames. As we saw before, we like the long layout or format because each column is a variable, each row is an observation. So with the purely long format, you have one column for the observed variable, and the other columns are the, you know, ID variables. And, you know, like I said before, many of our functions have been designed assuming that you have this longer formatted data. So therefore, we need to make sure that our data is in that format. And we'll do that here in this tutorial. So just another view of what the wide versus long looks like. And to get started, we need to make sure that our R environment is ready to go. So if you haven't used these two packages before, and we will need both of them, we need to install the Tidier and the Diplar packages. So I know I already have these installed in my R environment, but if you do not, then you would use the install.packages function. And just as we get started, I just want to point out that I've added a source document to my RStudio console. And this is good because you can document what you are doing throughout the process. So this will serve as some documentation that you can reference, share, go back to, and hopefully you've documented all of the steps that you've taken to, you know, in this case, you know, clean up your data, make it tidy. You could also use this for any data analysis that you're doing. So I'm going to work within our source, our source bin, and then run things within our console. And this allows me to add like comments. So as they've, you know, indicated in the lesson, we add a comment that the first step you need to do is you need to install your packages, right? So we tell it we need to install packages, Tidier and Diplar. That's a comment that we've added, and then you know you would your next comment could be load the libraries. So I will do that now. So I'm going to load my library Tidier. Run, and we see it run in our console. And I'll run our library Diplar. I did get some warning messages. It's just telling me about, you know, the difference in the R versioning. You may or may not see these when you run or load your two libraries. All right, another thing we need to do is we need to read in the Gapminder data set, which we don't see in our lesson here because they've done that in the previous lesson. So we need to do that before we can start looking at our Gapminder data frame. All right, so let's read in the Gapminder data set. And to do this, we're going to use the function read.csv. So we're going to create a data frame called Gapminder. And we're going to pull in that read.csv from our data folder and we want our gapminder underscore data.csv, and we'll run that. And we see that our data has successfully loaded. We see that because it is shown up in our global environment with our gapminder data. So we can also do something that we did similarly on the terminal before, which is, you know, kind of look at what we're looking at. So we use the function str to take a look at this object, and we see that our data frame has those 1,704 observations with 6 variables, or 6 variables being the country, year, population, continent, life expectancy, and GDP per capita. So great. So looking at, you know, we've looked at this data a little bit. Is this gapminder, you know, data purely long, wide, or some intermediate format? So I'll give you just a second to think about what do you think about our gapminder data that we're working with right now? Yeah, so this gapminder data set actually is in an intermediate format. So look at what the lesson plan says. Yes, the original gapminder data frame is actually intermediate format. It's kind of, it's not purely long, it's not purely wide. You know, since it's not long because it has these multiple observational variables, the population, the life expectancy, and the GDP. And sometimes, you know, as was this data set, we have multiple types of observed data, and somewhere in between. We have these 3 ID variables, and we have 3 observational variables. So this intermediate format can be, you know, preferred despite we don't have all our observations in one column, given that, you know, those 3 observation variables, the population, life expectancy, and GDP, they all have different units. And there are a few operations that would need us to make this data frame, you know, any longer. So, you know, while using many of the functions in R, you usually do not want to do, you know, mathematical operations on values with these different units. So using the purely long format, a single mean for all of the values of, you know, the population, life expectancy, and the GDP, they would not be meaningful since they return the means of 3 values with 3 incompatible units. So the solution is we must first manipulate the data either by grouping, which is taught in another lesson, or change the structure of the data frame. And that's what we're going to do. And we'll actually look at an example of calculating means later. But we need to change the structure of our data frame. So that's where we're going to come in to go from a wide to a long format. And since the current gapminder data is this intermediary, and it's nicely, you know, formatted, we want some real data, you know, some real, you know, our own research data, for example, that's not so well organized. So we're going to start with a wide format version of the gapminder data set. I suggested that you downloaded this prior to today, or prior to today's session, but I'll walk through how you can download it into our data folder right now. So again, we have this wide version of the gapminder data set that we can right click on and save as. So make sure we are in our data folder, and we have our gapminder underscore wide data. Again, we want to make sure that we read in comma separated values so that we can create a nice, you know, we can get our columns and our rows. So I will save that and watch it pop up in our files console within OpenRefine. So again, we'll load the data file and look at it. And just as a note here, we don't want our continent and country columns to be factors. So we will use the strings as factors argument when we read in this data set to disable that. And by default, when building or importing data, the columns that contain, characters, text, are converted into factors. But we want to keep these columns as characters or these plain strings, so we'll use this argument. So we will create a new data frame within our studio called gap wide, since we're working with wide format data. And we'll read in our new CSV, so data, and then data, and then, oops, make sure we pull in our Gapminder wide. Oh, I forgot my quotes. That's why it wasn't working. So remember our quotes, and then we can type out data and get our two options for the spreadsheet that we have. So we pull in the wide.csv. And then we need to make sure that we include the strings as factors argument, and make sure that's false. And then do that. So we see that we've created a new gap wide with 142 observations and 36 variables. Again, we could look at this with our STR, look at our new data frame that we created, and yes, we can see that it's in this, kind of wide format. All right. So in the lesson, they have a nice view of what, kind of we're looking at here. And to change this very wide data frame layout back to that nice intermediate or longer layout that we were using before, we will use one of the two pivot functions from the tidyr package. So to convert from wide to longer format, we will use the pivot longer function. And pivot longer makes data sets longer by increasing the number of rows and decreasing the number of columns, or lengthening your observation variables into a single variable. So there's a nice illustration of how they've taken the wide format. They've parsed out, selected columns. They've converted column names to columns, and then pieced it back together with new column names with key and value arguments. So we're going to use this kind of this template, the pivot longer data, what columns we want to look at, what convert column names to column, and then this name columns with key and value arguments. So that's kind of the template that we'll be working with our data. All right, so from our wide Gapminder data, we're going to create yet another data table called gap long, and we'll pull in the gap wide data, and we're going to pipe that through that template that I just kind of walked through using the pivot longer argument. So first we need to indicate the columns. So we'll be using, the columns to pivot into this longer format. So we're going to tell it we want the columns that start with this pop, our population, starts with our life expectancy, and starts with our GDP per cap. Okay, those are the columns. So the starts with argument to select all of the variables that start with the desired character string. Then we will use the names to for naming the column that will contain the new ID variable. We'll call that obs type year. And then the values to for naming the new amalgamated observation variable, we'll call that obs value. So we supply these new column names as these strings. So we do the next argument, which is names 2, which we will be calling the obs type underscore year. And then we want the values to this obs value for, again, for naming the new observation variable. And if we run that line of code, we can then use our str to double check that we've created the right thing. So we look at our gap long frame. And we see that we have a longer format. We've increased the number of observations and decreased the number of variables. So we have a row for our continent, our country. We have this observation type, and then the observation value. So we're also going to use an alternative. I'll give you an example of an alternative syntax, which you could use the dash symbol to identify which variables are not to be pivoted. So there's 2 ways to do this, and that's this second example, which would give you it's two ways to do it. So I'll just highlight how that works as well and type out this next example, which is doing the exact same thing that we just did, but it's a different way to think about it. So if we want to create that gap long from our gap wide, we can again pipe it through this pivot longer function. And then instead of telling which columns to include, we're going to indicate the columns to not include, to ignore. So it will pivot everything except the continent and everything but the country. But we still have to use the same names to arguments and values to arguments to rename our new column heading. So we still want to create an obs type year and the values to obs value. And then we run that and we get an error to see where the error occurred. And it's another spelling error. So we can go back to the code that we ran and make sure that continent, it's also tagged right there for us, make sure that continent is indeed spelled right, and we'll run that and nothing popped up again. So then we can run our str on our new, or rerun gap wide, or excuse me, run the gap long. And we get the same thing that we saw earlier, right? So those were two examples of how we could use the pivot long function to separate, our columns out. All right, yeah, that may seem, trivial in this particular data frame, but sometimes you'll have, one ID variable and 40 observation variables with these irregular variable names. So the flexibility of whether you wanna call out specific columns or tell it columns to ignore is good flexibility to have. All right, so if you noticed, our obs type _year column actually contains two pieces of information, the observation type and the year. So it's combining the population with the year, the life expectancy with the year, the GDP and the year. So we can use another function, separate, to split the character strings into our multiple variables. So using our gap long data frame, we're just updating our data frame as we go. We'll pipe in our data. Oops. We'll pipe that through our function separate. And we want to take that column name, obs type _year, and we want to put that into multiple columns. We want to pull out the obs type since they're all different, and then we'll pull out the year. And then we have to indicate how these are separated. So we'll use the separate, or the sep indicator, to indicate what has been used to combine these. And we need to look at the printout of our data, and we see that it's using an underscore to combine these observations. So we see a population underscore the year, GDP underscore the year. So in our code, we'll indicate that it should look for the underscore to parse out that data. So we'll run that. And then we also need to ensure, and we actually see that we've added a variable to our gap long, but we also want to make sure that that gap year column, that gap long year column is a number. So we need to create, we need to make sure that that's an integer. So we'll take our gap long data and focus on the year column, and we want to make sure we want to do it as, we can scroll through these to find out what all these different as functions do, all the way down to where we can find it as integer. So this creates objects for the type to make sure it's an integer, make sure it's a number. Wonderful. As integer, and again, we just need to specify that this is the column we want, the year column. So I'll run that. And of course, we can continue to just check in with our data as we go to ensure that we've done that. And we have, as we can see, we have a new column for the year, and it indicates that it is a integer. Wonderful. All right, so I said we would get into some example of how this long format is actually is good to use when doing data analysis. So we want to use our gap long data frame to calculate the mean life expectancy, population, and GDP per capita for each continent. And they've given us a hint here to use these two other functions called group by and summarize. And those are from this diplar package. That's why I had you guys load that library at the beginning as well. If you're not familiar with those functions, you can check out the diplar lesson, but we'll just use them to highlight how easy it is to write one line of code to get the mean of each of these items. So I'll give you a minute to think about how you would craft that line, and then we'll walk through it together. All right, so since our lesson kind of has us most of the way there, we can really take that information and craft our line of code. So we're using the gap long data frame, right? And we're gonna pipe that through these two functions. So first we're gonna use the group by. And as we get a little information in our RStudio, it takes an existing table and converts it into a grouped table where operations are performed by group. So we will get the means of each of the things that we indicate. So we want to group by continents. We're looking for the mean of the 3 variables for each continent. So we'll make sure we spell that right from our data frame. Continent, and we want to do it for each of our observation types. We haven't pulled those out in any way. They're still all under this one column called obs type. So we regroup by that, and then we want to pipe it through the next function, which is the summarize. Which creates a new data frame. It will highlight how we have parsed out our data, and it will contain the groupings for the variables that we want. So we're looking for the means, which equal the mean of our obs value. So look for the obs values. So we'll look for the values in each of our obs types, and it will calculate the mean for each continent. All right, so we run that, and look, we get a nice tibble, a new data frame that has organized our data, categorized our data by continent, and then listed the mean for each of the GDP, the life expectancy, and the POP. So it's a great way that you can use R and a nice, tidy data frame to easily do some calculation on your data. And we can easily see that, looking at the GDP and the life expectancy, as the GDP increases, as does the life expectancy, roughly. Great. So it's always good to check our work. So we're going to use the second pivot function, the pivot wider, to now widen our observation variables back out. So pivot wider is the opposite of the pivot longer. It makes a data set wider by increasing the number of columns and decreasing the number of rows. So we can use pivot wider to pivot or reshape our gap long to the original intermediate format or that widest format. So let's start with the intermediate format. So the pivot wider function takes names from and values from arguments. To the names from, we supply the column names whose contents will be pivoted into new output columns in the widened data frame. And the corresponding values will be added from the column names to the values from argument. So before we were using names 2 and values 2. Now we're spreading back out to a wider function. All right, so we're going to create a new data frame called gap normal. Gap normal. You can be calling these you can call these anything you want. I'm just coming up with some names to call these data frames, but you could be calling these anything you want, and then piping in the functions and arguments as they are. All right, so creating our gap normal, we're going to take that gap long data frame we created. We're going to pipe that through our function pivot wider, which we see down here, increasing the number of columns and decreasing the number of rows. Wonderful. And we're using the names from, right? Again, to supply the column name whose contents will be pivoted into a new output column. And we want those from the obs type. And then the values from. Which is our obs values. Run that. And then we can look at some information about our gap normal that we've created. So we can use dim, which will retrieve or set the dimensions of an object. So we're going to look at the dimensions of our gap normal data frame. We see that we have that original 1,704 observations and 6 variables that we started with. We can compare this. We could either do this in the console, or we can look over in our global environment and quickly see that the gap normal and the Gapminder are very similar. But just for sake of demonstration, we'll look at the Gapminder using the dimensions, and we see that it's as the same. We also can look at the names of our columns. So we're going to use the names function, which will get or set the names of an object. So we want to get the names in our gap normal. We see that it's continent, country, year, GDP, life expectancy, and pop. And then we can do the same thing, names for our Gapminder data frame. And we see it's very close. It's very close, but it's very close. So now we have this intermediate data frame, gap normal. It has the same dimensions as the original Gapminder, but we see that the order of the variables is different. So we see that this starts with country, year, pop, continent, life expectancy, and GDP. So let's fix that. That before checking if they are all equal. So we can do that. We can do that by taking our gap normal, and with our gap normal, we will make the names. We want to set the names the same as the Gapminder. So we tell it we want it to match the Gapminder. And then we can use all equal, which is a utility to compare our objects, testing near equality. If they're different, a comparison is made to some extent. and a report of the differences is retrieved. So we used all equal, and then we compare the gap normal to the Gapminder. We run that, and we get some information about how they're pretty close, but we see that there's some mismatches within our data frame. So let's look at what's happening here. We can use the head, the beginning of our data frames, to inspect what's happening. So we'll look at the gap normal head. All right, so we see that our gap normal data frame is sorting by continent first. That's why Africa is listed first. So let's see what's happening with our Gapminder data. We see that the Gapminder data was originally sorted by country, then year. So first we were sorting by country. A couple lines here. So let's make sure that these line up. So we can use the arrange function to help us do this. So we're gonna make the gap normal data frame match the Gapminder data frame using arrange. So again, with our gap normal data, we'll pipe that through the function arrange, which orders the rows of a data frame by the values of the selected columns, right? So we'll use arrange, and then we want to make sure that we're sorting by country, then year. Pipe that, run that through, and then we'll use our all equal again, all dot equal utility to then compare our gap normal and our Gapminder, and that's great. We have gone from the longest format back to that intermediate, and we didn't really introduce any errors in our code, which is wonderful. You are more than welcome to continue on with this lesson, but I hope you have seen how using the pivot longer and pivot wider has helped us arrange our data tables in a way that we wanted. So just to end our session today, the framework of tidy data makes it easier to get data in a useful form for analysis. We saw that when we looked for the mean of some of our observations, and it provides a useful framework for critiquing existing functions. So the R package Tidier provides functions to help you organize or reshape your data into a tidy format. So we use pivot longer to go from that wide to a longer format, and then we use pivot wider from the long to the wider format. And remember, good data organization from the start to help facilitate your analysis later. You can use RStudio to create and manage your projects with consistent layout, and that nice documentation console within RStudio we can save, and it becomes our documentation folder to document all of the steps that we went through in our analysis. Or not our analysis, but our cleaning process. So you could use that for later. If you are looking for additional training, the data carpentry, software carpentry, and library carpentry lessons are fully open, and you can walk through those lessons on your own. There's also some really nice articles out there about tidy data, including the one I mentioned from Hadley Wickham. We do have some upcoming data management online seminars. So next week we'll be talking about OpenRefine, doing some cool things with data cleaning, data organization in OpenRefine. And at the end of the month, we'll be talking about data horror stories. So thank you for joining today. The recording and the slides will be posted on our website. You can watch all of the crude programming we went through today. But I would appreciate your feedback on today's session. So please fill out the survey at the link provided on the slide.